Hello students, myself Sukumar Giri, faculty in the Department of Statistics, Barakpur Rashtraguru Surendranath College. Today I will discuss the topic on chi-square distribution. This topic which I will discuss today is specially designed for Sem-III Statistics General students. It helps the students of statistics honors also. First, we have to know how the chi-square distribution form from normal distribution. Let x be a continuous random variable follows normal distribution with parameters mu and sigma square. Let us consider a new variable z, that is z equal to x minus mu by sigma follows standard normal distribution, that is normal distribution with mean 0 and variance 1. Then z square equal to x minus mu by sigma whole square follows chi-square distribution with degree of freedom 1. Chi-square distribution with 1 degree of freedom. Degree of freedom means number of free variables. DF means degrees of freedom. Let xi follows normal distribution with mean mu and variance sigma square, where I equal to 1, 2 up to n. Then xi minus mu by sigma. Let us consider a new variable zi, which is x minus mu by sigma follows normal distribution with mean 0 and variance 1, where x1, x2, xn are independent random variables. Independent random variables. Therefore, zi square equal to xi minus mu by sigma whole square follows chi-square distribution with 1 degree of freedom. Summation zi square summation over I equal to 1 to n equal to summation over I equal to 1 to n xi minus mu by sigma whole square follows chi-square distribution with n degrees of freedom. Also, note that if xi follows normal distribution with mean mu I and variance sigma I square, xi follows IID normal mu I sigma I square. IID means independently and identically distributed variables. Then let us consider a new variable zi equal to xi minus mu I by sigma I follows standard normal distribution, that is normal distribution with mean 0 and variance 1. Then zi square equal to xi minus mu I by sigma I whole square follows chi-square distribution with 1 degree of freedom. Therefore, summation zi square summation over I equal to 1 to n equal to summation over I equal to 1 to n xi minus mu I by sigma I whole square follows chi-square distribution with degrees of freedom n. Now, the PDF of chi-square distribution is given by, let x follows chi-square distribution with degrees of freedom n. Then the probability density function of x is given by f of x equal to 1 by 2 to the power n by 2 gamma n by 2 into e to the power minus x by 2 into x to the power n by 2 minus 1, where 0 less than equal to x less than equal to infinity. This is the PDF of chi-square distribution. Next, mean. We have to find the mean of chi-square distribution. Mean of x, that is expectation x, equal to integration over x into fx dx equal to 0 to infinity x into 1 by 2 to the power n by 2 gamma n by 2 into e to the power x minus x by 2 into x to the power n by 2 minus 1 dx equal to 1 by 2 to the power n by 2 into gamma n by 2 integration 0 to infinity e to the power minus x by 2 into x to the power n by 2 plus 1 minus 1 dx equal to 1 by 2 to the power n by 2 into gamma n by 2. Using gamma integral, we get gamma n by 2 plus 1 by half to the power n by 2 plus 1 using gamma integral. What is gamma integral? Integration 0 to infinity e to the power minus x into x to the power into the integration 0 to infinity e to the power minus alpha x, where alpha is a constant, into x to the power n minus x to the power p minus 1 dx equal to gamma p by alpha to the power p. Using this gamma integral, we get expectation x equal to 1 by 2 to the power n by 2 into gamma n by 2 into gamma n by 2 plus 1 equal to gamma n by 2 into n by 2 by half to the power n by 2 plus 1. Since gamma p equal to p minus 1 into gamma p minus 1, where p is not an integer. Therefore, expectation x equal to n. N means degrees of freedom of chi-square distribution. Hence, the mean of the chi-square distribution is n. Now, we have to find the variance of the chi-square distribution. Variance x equal to expectation x square minus expectation x whole square. First, we have to find expectation x square. Expectation x square, now expectation x square equal to integration 0 to infinity x square into 2 to the power n by 2 gamma n by 2 e to the power minus x by 2 into x to the power n by 2 minus 1 dx equal to 1 by 2 to the power n by 2 gamma n by 2 integration 0 to infinity e to the power minus x by 2 into x to the power n by 2 plus 1 minus 1 dx equal to gamma n by 2 plus 2 half to the power n by 2 plus 2 into 2 to the power n by 2 into gamma n by 2 using gamma integral. We get this result equal to n by 2 plus 1 into n by 2 into gamma n by 2 by half to the power n by 2 plus 2 to the power n by 2 into gamma n by 2. Gamma n by 2 cancel. N plus 2 by 2 into n by 2 into 2 to the power 2 square, that is 4 into 1 equal to 2 into 2 4 cancel, n into n plus 2. Therefore, variance x equal to expectation x square minus expectation x whole square. Expectation x square equal to n into n plus 2 minus expectation x equal to n expectation x whole square, that is n square equal to n square plus 2n minus n square equal to 2n equal to 2 into degrees of freedom. Therefore, the variance of the chi-square distribution is twice n, that is twice degrees of freedom. Next, moment generating function of the chi-square distribution. Moment generating function of chi-square distribution, that is MGF. How to find the MGF of chi-square distribution? Mxt equal to expectation e to the power tx, where x follows chi-square distribution with n degrees of freedom, equal to integration 0 to infinity e to the power tx fx dx, equal to integration 0 to infinity e to the power tx into 1 by 2 to the power n by 2 gamma n by 2 into e to the power minus x by 2 into x to the power n by 2 minus 1 dx equal to 1 by 2 to the power n by 2 into gamma n by 2 integration 0 to infinity e to the power minus x by 2 into 1 minus 2t x to the power n by 2 minus 1 dx. Using gamma integral, we get 1 by 2 to the power n by 2 into gamma n by 2 into gamma n by 2 divided by 1 minus 2t by 2 whole to the power n by 2. 2 to the power n by 2, 2 to the power n by 2 cancel, gamma n by 2, gamma n by 2 cancel, equal to 1 by 1 minus 2 to the power 1 minus 2t to the power n by 2 equal to 1 minus 2t to the power minus n by 2, where 2t less than 1. Therefore, the moment generating function of chi-square distribution is 1 minus 2t whole to the power minus n by 2. Next, characteristic function of chi-square distribution. Characteristic function of chi-square distribution. It is denoted by phi x t equal to expectation e to the power I into tx, where x follows, x being a continuous random variable, follows chi-square distribution with degrees of freedom n. Phi x t equal to integration 0 to infinity e to the power I t x fx dx equal to 1 by 2 to the power n by 2 into gamma n by 2 integration 0 to infinity e to the power I t x into e to the power x by 2 into x to the power n by 2 minus 1 dx. Using gamma integral, we get 1 by 2 to the power n by 2 gamma n by 2 we make an adjustment here, e to the power x by 2 into 1 minus 2it into x to the power n by 2 minus 1 dx equal to 1 by 2 to the power n by 2 into gamma n by 2. Using gamma integral, we get gamma n by 2 by 1 minus 2it by 2 whole to the power n by 2 equal to 1 minus 2it whole to the power minus n by 2. Therefore, the characteristic function of chi-square distribution is 1 minus 2it whole to the power minus n by 2. Next, cumulant generating function. Cumulant generating function of chi-square distribution is denoted by kxt equal to log mxt. Mxt means moment generating function of x equal to log 1 minus 2t whole to the power n by 2 equal to n by minus n by 2 into log 1 minus 2t equal to n by 2 2t plus 2t square by 2 plus 2t whole to the power q by 3 plus 2t to the power 4 by 4 plus dot 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 logarithm series. Now k1 equal to coefficient of t to the power 1 by 1 factorial in capital KXT equal to n small k2 equal to coefficient of t square by 2 factorial in kxt equal to four 2 n k3 equal to coefficient of t cube by 3 factorial in kxt equal to 8n k4 equal to coefficient of t to the power 4 by 4 factorial in kxt equal to 48n. Therefore, mean equal to k1 equal to n, variance equal to mu2 equal to k2 equal to twice n, mu3 equal to k3 equal to 8n. mu 4 equal to k4 plus 3k2 square. k4 equal to 48n plus 3 into k2 square, 2n whole to the whole square equal to 48n plus 12n square. Beta 1 equal to mu 3 square by mu 2 cube equal to mu 3 equal to 8n square by 2n whole to the power 3, 64n square by 8n cube, 8 equal to 8 by n. Beta 2 equal to mu 4 by mu 2 square, mu 4 equal to 48n plus 12n square by mu 2 square, mu 2 equal to 2n, 2n whole to the power 2, 4n square, 12 by n plus 3. Now skewness equal to which is denoted by gamma 1 equal to root beta 1 equal to root 8 by n, which is greater than 0. Therefore, the chi-square distribution is positively skewed. Positively skewed. The diagram of positively skewed distribution is like this. Next, kurtosis. Kurtosis, which is denoted by gamma 2 equal to beta 2 minus 3 equal to 12 by n plus 3 minus 3 equal to 12 by n greater than 0. Therefore, the distribution, the chi-square distribution is leptocratic. Next, mode of the chi-square distribution. Mode. Let x follows chi-square distribution with n degrees of freedom. Then the PDF of x is fx equal to 1 by 2 to the power n by 2 into gamma n by 2 into e to the power minus x by 2 into x to the power n by 2 minus 1 equal to c into e to the power minus x by 2 into x to the power n by 2 minus 1, where c is a constant, c equal to 1 by 2 to the power n by 2 into gamma n by 2. Mode is the solution, mode of the distribution is the solution of f prime x equal to 0 and a double prime x less than 0. Fx equal to c into e to the power minus x by 2 into x to the power n by 2 minus 1 log fx equal to log c minus x by 2 plus n by 2 minus 1 into log x. Differentiating with respect to x, we get f prime x by fx equal to 0 minus half plus n by 2 minus 1 into 1 by x. Since f x not equal to 0, f prime x equal to 0 implies that n minus 2 by 2x equal to half, implies that x equal to n minus 2. It can be easily seen that at the point x equal to n minus 2, f double prime x less than 0. Therefore, the mode of chi-square distribution is n minus 2. Now, Carl Pearson's coefficient of skewness is given by skewness equal to mean minus mode by standard deviation equal to n minus 2 by root over twice n equal to two by root 2n equal to root 2 by n. Next, additive property of chi-square distribution. Additive property of chi-square distribution. The sum of chi-square variates is also a chi-square variate. The sum of chi-square variates is also a chi-square variate. More precisely, if xi I equal to 1, 2 up to k are independent chi-square variate with ni degrees of freedom, then the summation over I equal to 1 to k xi is also a chi-square variate with summation over I equal to 1 to k ni degrees of freedom. The converse is also, the converse of the theorem is also true. Okay, I finish my today's lecture.